Thank you. Good afternoon, everyone. So my name is Yoamel Milián-García, and I was Doctor Fellow in the HANA Lab. And today I'm going to be talking about eDNA metabarcoding for biosurveillance of invasive alien species using saturated soil trap solutions. And I would like to start by highlighting the two most critical effects of invasive alien species. The first one is on biodiversity, where negative effects of invasive alien species are considered the second cause of biodiversity extinction, only second after habitat loss. In 2005, so 54% of animal extinctions documented by the IUCN implicated negative effects of invasive alien species. And we cannot say that the rest of the species were not affected, simply we don't have that information in the other cases, or in most of the other cases. The second negative effect is on the economy. In Canada only, the cost estimated with mitigation effects and management costs of invasive alien species totals $187 million per year. And the projection estimates just an increase of up to 34.5 billion, which is quite significant. So, given these effects, the earlier we act in detecting the species, so the better for mitigating these negative effects, and the longest it takes to act, so the larger the area occupied by the species and the bigger the impact on the biodiversity and economy. So currently in Canada there are 272 regulated species by the government. So this includes only the terrestrial invasive alien species in this case, and includes the ones that are already known to be established in the country, plus those potential invasive alien species. If we break down these numbers, the vast majority of them are insects. So CFIA is primarily responsible for the biosurveillance of these invasive alien species, the terrestrial ones, and current biosurveillance methods heavily relies on morphological identification, which is not scalable, requires one-on-one identifications, and also taxonomic expertise on a wide range of taxa, which is scarce these days. So in this context, eDNA molecular-based detections is continuously being explored to establish a scalable and cost-effective protocol for biosurveillance. eDNA metabarcoding, as we have been discussing already, has become the method of choice in the molecular space, as it allows for a cost-effective and multi-species identification. But the routine use of this method in the regulatory context requires thorough validation, as has been considered a limitation. And as we learned earlier today, so validation can be taken at 4 different categories. So experimental validation, comparative morphological ecological validation, bioinformatic validation, and statistical validation. And in this work, we try to touch on at least 2 of these categories. So with 2 main objectives here. So the first one is to compare outputs generated from 2 bioinformatic pipelines out of the 31 already established, as was mentioned earlier today. And the second one was to compare a morphological-based detection against molecular-based detection when that information was made available to us. To accomplish these goals, so we processed all the samples received by our lab from the CFIA. And all these samples were collected across southern Ontario and represent the collection fluids of each of the linear funnel traps deployed by the CFIA between the 2017 and 2022. So this is how the traps look like in this case. And this current program is part of the biosurveillance led by the CFIA. And as I mentioned, so our specific samples are the collection fluids of each of these linear funnel traps that in this particular case are salt trap solutions. So salt trap solutions, because they have been using this over alcohol-based collection fluid, given the advantages of these solutions over these alcohol-based collection fluids, specifically lower cost, less storage space requirement, low toxicity to human, which is important because most of these traps are deployed in public spaces, fewer regulatory constraints for laboratories and inspectors, non-flammability, and lower evaporation rate. From the solution on, the methods are quite standardized in our lab, so we filtered all the material in that solution, extract DNA from those filters using commercial DNA extraction kits, and conduct library preparation for DNA metabarcoding, which in our case consists in 2 PCR steps, 2 cleanups, and then high-throughput sequencing using Illumina MySeq. The output, so the raw data out of the high-throughput sequencer, was analyzed using two bioinformatic pipelines, in this case, Invasive and MetaWorks. And the idea was to generate a species list with the highest confidence possible that was compared against the list of pests regulated by Canada. And we highlighted all the instances in which we got any hits in this case. So let's take a look at the results. So here we are summarizing the number of sequence reads generated from all these samples in all these collections, the number of exact sequence variants, and the number of species that we were able to classify. So as you can see, we got a range of sequence reads from around 4 million up to over 45 million reads, with the higher number of exact sequence variants, around 10,000 genetic variants, and the range of species varied between 35 and 673. We also determined whether or not that species richness was enough and maximized, given the sequencing depth that we use in this case, and we got saturation of all the rarefaction curves that we built in this case. And that is important because we, in the context of invasive alien species detection, these invasive species are expected in many cases to be in lower number compared to native species, so the amount of DNA is expected to be in lower concentration, maximizing the capacity of sequencing and recording diversity in a given sample is critical to increase detection probability in this context. So let's take a look at how many of those species were hits against invasive alien species, and we break down these numbers based on our two bioinformatic pipelines, and that's what you can see here in the bottom of the image. So for MetaWorks and Invasive, and the numbers are also summarized in the table for your convenience. And there are two elements that I would like you to notice here. First, the maximum number of species detected, invasive alien species based on molecular detections, was 5. Second, that MetaWorks picked up the higher number of invasive alien species compared to Invasive, which is more evident if we zoom in these particular collections and try to quantify these individual detections. So in these bar plots, every bar represents a sample, the different colors represent the different invasive alien species we detected, and as you can notice, 25 molecular individual detection based on the MetaWorks pipeline compared to 12, so double the number of molecular detection. But not only with MetaWorks we picked up the higher number of molecular detections, also the higher number of coincidences between molecular detections and morphology. And that's what we are trying to summarize here with the Venn diagrams. In blue are representing the molecular detections, in red the morphological detections, in blue, and in red the molecular detections. 11 out of the 25 molecular detections were resulted in coincidence between molecular and morphological detection. So these were cases where we got the molecular detection and also had physical evidence of the specimen in a given sample. So, you might have noticed already that I have been comparing all the time absolute number of detections, and the reason is because we are more interested in these absolute numbers than in the statistical significance of the differences in these cases, given the higher biological impact that every of these species has on biodiversity and economy specifically. So let's take a quick look at what these species are. So we detected, as I said, 5 invasive alien species based on eDNA. 3 of them are coleopterans, 1 Nycterans, so the coleopterans, emerald ash water beetle, the Japanese beetle, and the golden longhorn beetle. 1 Nycteran, the gray Phylloxera, and 1 Lepidopteran, the spongy moth. The emerald ash water beetle is a species native to Asia, was introduced in Canada in 2002. It's a wood-boring beetle. The larva feeds exclusively on ash trees. In the image you can see the kind of galleries that the larva can do and the cracks that it produces. So it is responsible for the tree mortality, and since the introduction of the species in North America has been responsible for the mortality of millions of ash trees. So significant impact of reduction of biodiversity and in the economy. The Japanese beetle, a species native to Japan, was introduced in 1939, so it's considered the most damaging pest of grass. The larva live in the soil, feeds on the roots of the grass, so can damage lawns, pastures, and golf courses, and the adults can also defoliate, so they have that defoliator capacity. The velvet longhorn beetle, so was first detected in Canada in 2002, is another wood-boring beetle. So it feeds on over 40 genera of broadleaf and conifer trees, also with a significant impact on biodiversity and economy. So the grape Phylloxera, feed exclusively on grapevines, specifically genus Vitis. It has a leaf galliform and a root galliform, with the root galliform being the most damaging form in this case. So it had a significant impact on the wine industry. And it's also responsible for the mortality of the grapevines. And last but not least, the spongy moth, was introduced in Ontario in 1969. So the larva feeds on hardwood and softwood trees, including the oak and maple trees. Is one of the worst defoliators, and in fact is listed as one of the 100 worst invasive alien species according to the IUCN. So given the significant impact of these species, having molecular methods in place that allows early detections are critical in this case. So in summary, we can say that eDNA metabarcoding of salt trap solution can be considered as an effective method for molecular biosurveillance, and it allows morphological detection when needed. Also, that MetaWorks and Engrave bioinformatics pipelines effectively allows invasive alien species identification, but MetaWorks have a higher success rate in this context. So, and with that, I would like to acknowledge the Canadian Food Inspection Agency that funded this project and made it possible, and the 100 lab members, especially Ashley and Morgan, for valuable support in the lab. With that, so I'd like to take any questions you